video over, let's see, like really dark in here, jeez. Anyway, a video going over electromagnetic force or electrostatic force, different names. Basically, forces that are caused by magnets or electricity, which creates magnets. So basically, one of the same thing. And this force is first and foremost very different than gravity, of course. You say it's not the same thing. It is different, right? But you're going to see pretty soon the equation is actually pretty similar looking, right? And I hope, wow, now it's way too bright. And I hope what you're going to say is, okay, so there's probably like patterns in nature, right? Like scientists, we notice there's a lot of patterns, certain things that appear to be similar. And yeah, that's an interesting thing that hopefully you're observing. But what I will point out first about gravity compared to the electromagnetic force is the electromagnetic force is way stronger, okay? Like, I mean, substantially stronger than gravity is, okay? And you might say, no, it isn't. Gravity's stronger. If I drop something, it falls. You live on Earth, okay? You live on a planet that has a mass of, what, almost 6 trillion kilograms, right? 5.972 times 10 to the 24th. That's a lot of mass, and you're right on top of it. Okay, so you feel gravity every day. You're used to it. If I put you in space, even if I put you only 1,000 miles above the surface of the Earth, you'd be like, wow, it's a lot less gravity. Okay, gravity is not a strong force. The electromagnetic force is considerably stronger. So that's kind of one of the first things I'd point out to you, all right, and hopefully be able to convince you of that here in a couple of minutes. We say gravity is basically a force between two objects that have mass, okay? And, you know, when we think about this and you say push or pull, any force can be thought of like that, okay? Electromagnetic force is not something is pushing it or something is pulling it. It's not gravity. It's not massive object. It's now charged object, attraction or repulsion, okay? So you don't need to be touching, right? The force does not need to be something pushing or pulling or gravity, okay? So just be aware. There's another major kind of force out there, all right? And again, the key here is charged particles. I say two. You could have many more than two, but to keep it simple, we stick with two, all right? You could make it more complex, just like gravity can get way more complex with more objects, but we don't want to, this is high school. This is not college. We don't want anything too crazy here, okay? So they say, well, what is charge? And charge is kind of a hard thing to describe, okay, without talking about magnets, truthfully. But I'll try my best to explain it in a way that hopefully makes sense. Basically, charge is a collection of either positives or negatives, which themselves are charges, right? And what this basically is imagine an atom, right? Everything is made up of atoms. All matter is made up of atoms. Atoms by default, normally, quote unquote, they are neutral. There is no charge, okay? Atoms have protons, atoms have electrons. Those two things are opposites in charge. Protons positive, electrons negative. If you ask why, that's a very good question. For this level of class, the answer is that's their charge. You want to know more about that, we got to start getting into some particle physics, and that gets a little messy. Okay, I'm not saying it's a bad question. I'm just saying I can't really talk about particle physics in this. But if you have those questions, feel free to ask, right? Write in the comments, email me, whatever. Stop by after class, okay, whatever you need. All right, it's a bit of a complex question to answer. Okay, the universe likes balance. Charges, the universe doesn't want them together. Or rather, let me rephrase that. The universe doesn't want charges. It wants them to cancel out. So atoms by default are neutral. Okay, we can create charges. There can be charges created in nature by energy taking those balanced charges and reconfiguring them so that now you have more positives on one side and more negatives on the other. So like a magnet, you say, how does a magnet get created? You're basically permanently creating atoms that are pointing in a direction that gives them charge. Okay, it's way more complex than that, but I want you to imagine it as pointing in this direction would make them positive, pointing in this direction would make them negative. You can freeze those molecules in a particular configuration, and that creates a charge. Gets a little messy, hard to visualize, so what's probably easier to start out with is the idea that you're either giving something electrons, you're giving electricity basically, or you're taking away electrons. Okay. If you take away electrons, what happens to you? You're losing negativity. You're going to become more positive. If I give you electrons, if you get more electrons, you have more negativity. You will gain a negative charge. Okay. For a non-physics class, this is an acceptable way to start out with it. Because if you're taking a physical science class, a very basics of science, this is acceptable. It gets more complex, okay, and this one certainly can be more tricky, okay. So don't feel bad if you're like, this is a little bit confusing, because it is. This idea of field lines is how the charges feel each other, interact with each other. Okay, so positive charges are giving off these field lines, which are basically, imagine like waves being sent out. It's not perfect. So what that means is two positives are sending out waves. Basically, they hit and they say positive, and they repel each other. Okay, charges want to be with opposites. Okay, it's like canceling itself out. All right. So if I have two positives, they're sending the waves out, and they say, I don't want to be near that. They repel. And as they get closer and closer, more force is needed to get them to approach. They don't want to be near each other. Okay. Two negatives, you think the energy is coming in, or rather not the energy, but the waves are coming in. This one's kind of harder to see, but because they're both like charges, they don't want to be near each other. They push away. Okay. You can right now experience this. Take two magnets that are the same pole, north and north, south and south, negative, negative, positive, positive. And if you put them close, they don't want to be near each other, whether it's the positive end or both negative ends. Okay. Now, if you flip one, negative, negative, positive, positive, negative, so positive, negative, they are attracted. And that might be easier to see because you see those field lines. One is sending it out, one's receiving it. That's a good combination. Hopefully that makes sense. It's a little bit messy. Okay. The analogy I would give is that these are yin and yang. They want to complete each other, right? So like a key and a latch, right, for like a gate or like a door, like a key and a door or whatever. They're made for each other, okay? And they lock in and they want to stay there. It takes energy to pull them apart, okay? That might be a good way to think about it. It's not perfect. But again, if you're taking a particle physics class, then this analogy is too simplistic. Okay, if you're new to this, if you're taking a physical science class in high school, this is probably a good start. At least I hope it is. Okay, and energy, of course, is going to be needed to pull them apart. If I did the opposite, like two gates, I'd have to push them together. I would have to put energy in to get them to work. Okay, in this case, negative and positive, they stick together, and then I need to pull them apart. I need energy. Okay, hopefully that makes sense. Okay. When we think about charge, again, this idea of electrons, giving electrons gets you more negative, taking away electrons gets you more positive. Okay, this is probably the easiest way to start with this. Again, I've kind of said this, but just keep that in your mind. All right, so if I take away electrons, more positive, give electrons, more negative. How can you do this? The shortest answer is you use energy. So either you take electricity, which is a flow of electrons, and you start basically providing charge to something, or providing a negative charge, I should say. The electrons are like, oh, let me flow out of this wire. This wire has a lot of electrons. I don't want to be in there. There's too many negatives. And it goes into something else, right? So, if I were to touch a piece of metal, right, there are electrons that go from my hand to that piece of metal. Not a lot, right? I don't generate electricity, but there's a little bit, okay? If I were to rub my hands together and touch something, higher probability I'd be shocked a little bit. You've probably experienced this where you're taking a sweater off, for example. Well, what happens when you take the sweater off? You might feel that static clinging feeling and hear the little, what do you call those? Little zapping noises, right? Because you are creating charge. That polyester, that plastic, I know this is weird, but like a sweater, if it's made of polyester is a plastic. So it's plastic you're wearing. When you pull that off, what happens? You create charge. And that's how you can get shocked. That's why you've probably been shocked by that before, because you've created a charge. Your energy of removing that, or putting it on for that matter, can create the charge. Okay? Basically, energy is moving electrons. Okay? By you pulling it on or pushing it off, whatever it is, that's how you create that. Okay? I give the analogy of a rock being pushed up a hill, this idea of potential energy. Okay, so when you're taking that sweatshirt off or whatever, right, there's energy you're using to pull it. And you might notice, again, when it kind of sticks, that static cling, you need to fight that, right? That's potential energy. You've created charge by doing that. When you get shocked, when you feel the zip, right, that's that energy being released. That's that charge equalizing, spreading out. And that's what the universe wants. It doesn't want that charge to stay there. It wants to spread it out. Hopefully that makes sense. So pushing it up the hill takes energy. You get it up there, now you have a charge. And now if I let the rock go, it'll go back down, right? That's the release of energy. So you build a charge and then you discharge it. Okay. Generally speaking, building a charge takes time, right? You don't build a charge instantly, at least not usually. So you're building a charge, building a charge, building a charge. I want you to imagine you get to the edge of the cliff and then it just falls. That's the discharge, electricity flowing very fast. How fast? Nearly the speed of light, which is a lot faster than you can pull your sweatshirt on or off. Okay, so hopefully that makes sense. Okay, this idea again of like what the universe wants. It doesn't want the rock to go up there. It doesn't want to increase potential energy, so I have to put energy in to create that condition. Okay, like charging a battery. Okay, and you might say, well, my battery doesn't die instantly. Well, yeah, you designed the battery to slowly drain for your devices. You don't want your battery to drain instantly. That could also explode. We don't want that to happen. Okay, but it's an analogy, right? All right, and again, you can always pause if you want to read through this, but I'm just giving you the important bits. Okay. We talked about charge, talked about this, right? And we already talked about this as the idea of repulsion, right? Repulsion to like charge is positive, positive, don't want to be near each other. Two negatives, don't want to be near each other. Negative, positive, attraction. Okay, that's that right there. Hopefully you're like, yep, I got that. Okay. Calculations, this is the part I kind of started out with, or rather I was leading us into that, saying this is where you might say, ooh, I see the connection. If you look at what's called Coulomb's law. Coulomb's law is just like the law of universal gravitation. You say, wow. I mean, it's different, right? But you're probably saying, wow, like that's pretty similar. Okay, it's not G anymore, it's K. And instead of M1, M2, now it's Q1, Q2. Yeah, they're behind absolute value bars. That's a little different, but it's pretty much the same equation. It looks very similar, and there's a reason, right? Looking at this, the units matter, okay? So Fe is in newtons. K is Coulomb's constant. You might be saying, why is it K? Why? What is this? Because Germans were very big in science. They still are, but really big in science. Turn of the century, 1800s, 1900s. A lot of German scientists. They got to name things. And the word K, or rather the letter K, is how most C words start in German. So if it's in English, it's C. Very good chance it's K in German. The word constant in English is Konstant in German. So anyway, a little linguistic trivia there. But a K, if you see a K in a math equation, a K in a science equation, probably constant, some constant. We know which one. Okay, and that unit, the unit for that are kind of messy. Newton meters squared per Coulomb squared. It basically lets you convert. It allows you to basically reconcile the units to get newtons. If you ask me why, it's a good question. I'm not going to say it's a bad question, but again, a little above the scope of this class, a scope of a physical science class. Okay. Basically, it's to make sure the units work together. You'll notice the value, 8.99 times 10 to the ninth, is way bigger than the gravitational constant. The gravitational constant, if you remember, is 6.67 times 10 to the negative 11. That literally is a 10 to the 20 difference. You say, how big is that? That I don't know, 10 to the 20, is that a big number? That is what? Nearly a billion trillion. Nearly. It's 100 million trillion. That's a lot. Okay, if I gave you that much money, you'd be pretty happy. Okay, big number. Okay, so the point is that this is way stronger of a force than gravity. Gravity is weak sauce compared to this. Okay, obviously you need to know how big the charges are, right? I mean, I'm not saying gravity is always weaker, but the idea is that generally speaking, this force can be way stronger than gravity. Okay, so then what is Q1, Q2? These are charges. And charges are measured in coulombs. A coulomb is a measure of charge. Okay, the more coulombs I have, the more charge I have. Coulombs can be negative because you can have negative charges, right? You can have positive charges, you can have negative charges. Okay, the absolute value bars just means basically make it positive no matter what. So if it's negative, it becomes positive. If it's positive, it stays positive. Interestingly enough, in my opinion, there shouldn't be absolute value bars here. Okay, that'll make more sense when we do some calculations. And if you're saying, well, who are you? You're just some high school teacher. No, I get you. I see what you mean. But there's a reason. And when I explain it, maybe you'll say, oh, I see. Anyway, so we need the charge of 1, charge of 2. Doesn't matter what order, right? A times B is B times A, okay? The unit has to be in coulombs, though. So if I give you millicoulombs, if I give you gigacoulombs, that would be kind of scary. You have to convert it, so make sure that's clear. R squared, we're looking at the radius length, the distance between the center of the objects, essentially. We usually just simplify it to the distance between, okay? I'm just giving you the truthful statement that a lot of times we're just going to say distance between. Technically, it's the center to the center of the other object, which might matter for objects this close, right? But if it's like the Earth and the Moon, it probably doesn't matter that much. It's probably going to be lost in what's called negligible difference, but that's a whole other conversation. But it's got to be in meters, so keep that in mind, all right? We'll do one practice problem here, and then I'll probably call this video, call it, because you're probably like, okay, he's been talking for a while. Hopefully you're enjoying it, but it is what it is. So if I have a 0.05 Coulomb charge, it's located 4 meters away from a negative 0.025 charge, Coulomb charge, calculate the force between the two objects, okay? You're just plugging numbers in, right? These problems are easy. We list out what we know, what we don't know. I know Q1, I know Q2. The fact that one is negative and one is positive means what? There's going to be attraction. Okay, so this is why I think we should not have the absolute value bars, because the absolute value bars mean it doesn't matter now, so now they're both positive. All right, you still know there's attraction, but in my opinion, it would make more sense to make it where this should be a force where either it's positive or it's negative. If the force is positive, what does it tell you? There has to be repulsion, because a negative times a negative is a positive, or a positive times a positive is a positive. If you had a negative and a positive, like this, what's a negative times a positive? Always negative, right? Which to me would mean that if your answer is negative, you know it's attraction, and if the answer is positive, you know it's repulsion. See, to me, that makes sense, right? But that's not how this is typically written. And yeah, that's my rant over. Anyway, radius of 4 meters, K is always the same, 8.99 times 10 to the 9th. And all you're doing here is plugging in numbers, right? So everything's in coulombs, yay, meters, yay, K is always K. I plug my numbers in, I make sure to do my math right, and what do I get? In this case, about 702,343.75 newtons. That's a lot of force, okay? If I had that many kilograms on both and they were 4 meters away, guess what? My answer would be like 10 to the negative 12, 10 to the negative 13 newtons. It would be a very tiny answer, okay? Because gravity is weak compared to electromagnetic force, okay? So hopefully that makes sense. So again, feel free to pause and try to make sure your math works out. Even if you know the idea, make sure you can do the math. In any case, have a great rest of your day, and see you in the next set of videos. Have a nice day.